Alrighty, looks like we have the streak breaker already. 1 day between hards, I guess. Well, at least this is a... I don't know if I should be happy that this is just a continuation of the previous one. Right, minimum cost to convert strings, part 2. You're given 0 index strings, source and target both of length n and consisting of lowercase English letters. You're also given 2 0 index strings, original and changed, and array cost, where cost I represents the cost of converting strings, original I to strings changed I. Now why should they? Much easier if they just gave us a 2D array, whatever. You start with a string source. In one operation, you pick a substring x from string. Ooh, pick a substring x and change it to y at the cost of z if there exists any index j such that wonder if there's a reason why this is substring rather than like a character. Okay, but it does seem like it's just letters. Okay. You're allowed to do any operations, but you're allowed to do any number of operations, but any pair of operations must satisfy either of these conditions. The substring picked in the operations are sourced from A to B and sourced from C to D, with either B less than C and D less than A. B less than C and D less than A. In other words, the indices picked in both operations are disjoint. The substrings picked in the operation sourced from A to B and sourced from C to D, with A equals C and B equals D. In other words, indices picked in both operations are identical. Oh, mama. This seems complicated. Return the number of minimum cost to convert the strings from source to target using any number of operations. Is it possible to convert? Return 81. Okay, let's just look at the examples here. ABCD to ABCBE. This is the same example as yesterday. So A to B costs 2, B to C costs 5. Really don't understand this actually. To convert ABCD to ACBE, do the following operations. Change substring source 1 to 1 from B to C at the cost of 5. So changing this B to C using this exchange, which costs 5. Okay. Change source C to C, or 2 to 2. So C to, okay, 2 to 2 just is referring to this interval. 2 to 2 to E, C to E using this thing, I guess, which costs 1. Okay, yeah. And then change that same thing from E to B using this thing, which costs 2. And then changing 3 to 3, D to E, which costs 20. Okay, so this seems exactly like yesterday. Okay, example 2, A, B, C, D, E, F, G, H to this thing. Okay, here we go. So original and change are not character arrays, they're string arrays. Interesting. So I can change BCD, so change this thing to CDE, which is target. That's fine, costs 1. And then, so that changed to CDE. And then E, so the back 4, the back 3, FGH needs to be GHH. So FGH can change to THH, and then THH can change to GH. This to be 135. Okay. Okay. Input 3. For example, 3, A, B, C, D, F, G, H, A, and then D's. This is impossible. Let me try to figure out what the hell the conditions are. The substrings picked in the operation source A to B and source C to D with either B less than C. B less than C. In other words, the indices picked in both operations were disjoint. Must satisfy either any number of operations, but any pair of operations must satisfy either source A to B and source C to D, either B less than C or D less than A. Indices picked in both operations were disjoint. Substrings picked in the operations are source from A to B and source C to D, where A equals C and B equals D. Substrings picked are either disjoint or identical. Source A to, so you can't pick overlapping things here. I think I understand. I think I understand. So like if there's, if you pick like these first three, you can pick those first three again, but you can't pick like 1 to 4, because that would be neither disjoint nor identical. So once you have an operation on a particular letter, you can either repeat that letter or skip to the last letter, skip to the next letter following the last. Interesting. Also interesting that they didn't have an example covering that case. Or I guess this is an example covering that case. Yeah, okay, this is an example covering that. BCD can be changed to DDD, and then DFG could be changed to DDD, but you can't do both because D is disjoint. D is not disjoint. Okay. Well, at least I understand what's going on. So it's 1,000 length. So this feels like dynamic programming, maybe. So you either convert or you move on. You either convert or move on. What lessons from yesterday can I pull up today? Be honest and say I don't think anything comes to mind. So yesterday I did a graph of the transitions. There's just too many transitions here, I think. So there's 100 possible changes. Each change possibly being as long as the string length itself. Cost being up to 10 to the 6th. Oh. Right. Give myself an hour to do this, or give myself an hour to ram into this wall. Okay, I think maybe looking at maybe example 2, kind of. So that's the source. Target is A, C, D, E, G, H, H. So it doesn't, so are all the things in source and target the same? I don't think so. Source at source at I and target I are probably equal in length, right? Surely they're equal in length. Source and target, original and change at I thought would be equal in length. It doesn't even seem like it. Source and target the same character length. The cost, length, original length, and change length are the same. Okay, that's fine. The original I.length. Okay, so yeah, they are the same length. So it's not like changing from A to 2Bs or something. Original I.length equals change I.length. But it's not guaranteed that they're all the same. Well, I guess that's this example. You have 3 to 3 and you have a 4 to 4 length exchange. All lowercase. Interesting. Wowzers, this is quite hard. So A, B, C. So I think I wonder. I think it's gonna be as easy as some of these exchanges where it's like FGH goes to THH and then THH goes to GHH. It's quite convenient there, but I don't know if that's how common that would be. So that's pretty common in the letter case. That's really how I have to approach it though. I think I have to approach it so that I break it up into the various lengths of the original to changed strings, and then consider each possible transition from defined values that are existent within the original and the change space. So like for every original 3-letter string, I try to connect it to try to find the lowest cost to the change 3-letter string. That is kind of the only things I can do. And obviously if it's the 1-letter case, then it's like from every letter, 1-letter string to every other 1-letter string in that space. It is going to be only 100 by 100 matrix, which is only slightly more than the 26 by 26 matrix of the previous problem, 26 letters starting, 26 letter ending. I think that's what I had to do. So I think it's going to be something like create low cost transition matrix where the I guess I should probably do first is kind of sort. So is that 100 by 100 or is 200 by 200 actually? I guess it's up to 200 by 200 because each possible space is all possible different starting points, all different possible starting all different possible starting values in either original or changed. Any string within original or changed is a starting value kind of, and anything in original and changed is the ending value. So it's up to like up to 200 by 200, which is something fine. 40,000. Let me think. And then map each of those strings to an index. Is it space array? How do I map each string to an index? I know I'm gonna screw up this part. This part is gonna be very suboptimal. Okay, so let's go all words. There's gonna be a dictionary that maps to a number. Is that right? So if I want to basically create all words be a string that includes everything inside original and changed and map that to a number. So the number can be used as the index into a matrix. So I want to use default dictionary, map each word as a key, the value is the index. I guess. Let's go ahead and say the what do I want to call this, integer index, the word num. I guess this is the word ID. For every word in original, if word not in all words of this word is equal to this word ID, increment the word ID. It's kind of the word count. And then similarly for every word in the changed word, not in all words for this new word is equal to this word ID. Word ID plus equals 1. So now word ID has all unique words, has count of unique words in word space defined by the original and changed. Okay. Well, I think I need to create my low cost transition matrix. Let's say it's infinity times word ID for everything in range of word ID. I think this is correct syntax. This is low cost is lowest cost transition between any two words. I think that's correct. I need to have, I think I need to actually have an array for the words itself so that I can map back. I can do the reverse mapping from ID to word itself. I'll do the unique words as an array. I wonder if this is better if I somehow segregate by the size. Probably not. It's probably just more complicated. I think I can just handle the generality of this. I probably need to define it based on the actual thing. So some of these has values that are based on the original and changed arrays and cost array. So for every, let's say n is the length of the cost array, which is the same as the length of the original or changed. So for every index, I'll say k in range n. Let's go ahead and take the O word, the original word, C word, changed word, and the current cost, current change cost. I'll say this is the x cost, exchange cost is equal to original at this index, changed at this index, and cost at this index. And then it will be low, get the indices into the transition matrix. So think it's using the dictionary to get the index right. So the original index is going to equal all words at the original word, and the change index is going to equal all words at the change word key. And then the low cost at the original index to the change index is equal to this exchange cost. Alright, I think that's okay-ish. I want to say I'm going to do a lot of comparisons of word lengths, so maybe I want to actually have for each unique word, I'll do unique lengths. Because that's probably going to be something I do pretty often here. So for each unique word I append to the array, and each word I append its length to the array. Okay, so from yesterday, I need to basically start with every possible word, consider how it transitions. So for k in range n, no. It's the word index, so I'll just use w index wind in range. I guess this would be, have the number of words. I guess that'd be word ID. In range word ID. Maybe I should call this word count. It's pretty much the same thing. Word ID is just the usage of word count at some points. I can do this as word num, w num. Increment the w num. I guess word num is probably. Okay. W none. W num. All words for this word is equal to w num. Change this. For every word index in range of word num. Okay, so this is considered the start. The start word is the unique words at this index. And then I need to consider all possible transitions. So this is heap, I think. Yeah, this is heap. So let me go ahead and just look back into yesterday's problem to verify how I made the heap. So is this thing heap is low cost? Yeah, sure. So it's going to be at the tuple where's the cost and the cost and the index and the destination index. Okay, so the cost here is going to be every neighbor of the thing, right? So it's going to be low cost from the start index to the neighbor index. The destination index is the neighbor index for every neighbor in range of also wnum if low cost from the start to the neighbor is infinity. So there is the transition there. Alright, I think that's the logic that I want here. Okay. Low cost for neighbor in range 26. Yeah, okay. Start heap with all current transitions from or create heap with all current transitions from start word. Yeah. Then I need to heapify heap. Once I do that, then I need to basically build it up, right? So I think it needs to be while heap exists, take out the lowest cost. Actually, what I call this thing? Total and current. Total cost of the path, current word index, heap hop, heap. Take current path cost and current word index from top of heap. And then for every, I think I need to do, I don't know if this is necessary to be honest. If total is greater than the current low cost between start and this current thing, and continue. I don't think this is necessary. We also wanted to, was it the 0 to 0? Low cost 0, low cost start to start 0. I don't know if this is necessary either. Total is greater than, okay, anyways. For every neighbor of this thing, for every other, sure, in range of the total word num index, Actually, is this right? Do I need the starting word? Start equals unique words. Low cost of start. Low cost should use the index. No, this is wrong. I think this should just be where we start. Start is the actual index rather than the word. I think start is every index. Start is every index, right? For every starting from start word index. To every neighboring word. I guess I don't need to compare. Don't need to compare lengths because it's already guaranteed to be the same length if there's a transition between them. I guess that's fine. For other in range wnum, if other equals start or other equals current or cost is infinity, right? Low cost between start. I guess where is it? Other and current other. Then continue. Skip it. So the part cost is the low cost between current and other. And then if the total path plus this extra part is less than the lowest cost between the start index and this other index, low cost between the start and this other index equals total plus part, and then heap push onto the heap the tuple does total plus low plus part, and then the other index. Okay. Alright, at this point, so lowest cost transitions between any original to any lowest cost transitions between any possible exchange has been found. I think that's right. So now it's just the dynamic programming part, I think. Maybe I should actually check that there's no crashes here. Okay. Seems reasonable. Maybe I can just print out the transition matrix. See how it looks. It's reasonable. So there should be 1, 2, 3, 4, 5 things. 5 unique 3-letter strings. So So there should be a 5 by 5 transition matrix. So this to this should cost 1. So BCD, so I think that's this one right there. This index 0 string, this is index 1, 0, 1, 2, 3 string. So row 0, column 3 should be 1, and then FGH to THH is 3, so this should be index 1, so it would be row 1 to row 1, column 2, row 1, column 2 is 3. Alright, this looks fine. Okay. So now it's just a matter of, I think it's a matter of dynamic programming maybe. It's like for every index in the source, I need to store the lowest cost to get to that index changed. For every index in the source set or target, find the lowest cost to get to that index. Yeah, okay. This should probably be DP for dynamic programming. I'll go infinity. What is n here? I'll say t num. T length is the target length, or length of source, I guess. So I think it should be probably like infinity times t length plus 1. This is dynamic programming. Cost array. Which stores lowest cost to change up to each index in the string, source target string. And then dp is going to be at 0 equals 0. Do I need to have a 2D array here? Generally, if there's other parameters besides just the input, like if you can only change the number of operations is a fixed number of operations, or there's a limit to it. But here's any number, so I don't need to keep track of how many operations have been done. So I don't think it needs to be a 2D DP matrix. It could possibly even be a 1D matrix. Nah. I think it has to be one-dimensional matrix. One-dimensional array. Okay. So for every index k in range t length, or is it range t length? Yeah, that's right. Okay. Mamma mia. Shucks cahoots. So if I'm at a certain letter in my source, let's say I'm at the starting letter A, I would need to see everything that starts with A, every matching string, every matching word in the change in the original or change space. That oh, if I need to see, original goes to changed. Did I need to have it add up? Could I just use the original space? Original goes to change. So A goes to B, and B goes to C. I guess I didn't need A goes to B, B goes to C, so I did need to have A goes to C. But I didn't need to have C goes to A. A goes to B, B goes to C. Yeah, it's easier for this square matrix, whatever. For K range T length. So anyways, if I'm at index 0, I'm trying to change something with A to something with this. It could be that it doesn't need to get changed at all, but every possible thing needs to be considered. So everything that matches starting with A, B, C, D, E. I guess there's only 200 things at most. All of them have to be considered. Ugh. All things must be considered. Okay, so let's go ahead and say the current cost up to now is going to be dp at this index. I could do something like if source at k equals target at k. So this is the same letter. And then current cost or dp at k plus 1 is equal, or say if source is equal to k and current cost is smaller than dp at k plus 1. dp at k plus 1 equals current cost. So this is kind of the trivial case where no change needed. Same source and target letter, and then update cost if current is lower. So if the current cost is like 0, you see that the source and target letters are A and A, so that means going to index 2, index this one plus 1 is the same cost if it's lower. which it would be for the kind of starting case where it's infinity up to every other index. Alright, now for the non-trivial case. So every possible thing. Fuck. Okay. Seems like this is gonna be really slow. Okay. Anyways, for every man, how slow is this gonna be? It'd be 1,000 by 200 by 200. 1,000 by 40,000. Guess that's 4 million, or is it 40 million? That might be too slow. Fuck. Oh well, let's try it. For every possible exchange, right? So it's gonna be for every W index in range of the word nums. So the current cost up to now is infinity, then I should just skip, should return it's impossible, right? Is that how I want to handle it? So if it goes up to here and says infinite. So for every word number, word index, so maybe this should be for every original index. Whatever. Word index in range. I'll say the word itself and the number of letters is based on the unique words of this index. That's unique words. Unique words. Yeah, unique words of this index. And the unique length. Unique lengths of this index. And then if it's impossible to do this, then I need to skip it if k plus word length is greater than or equal to the target length. Continue. I think that's right. I wonder if I should also do something where yeah, whatever. It's greater than or equal to or greater than. So if k is 0, word length is 1, source and target length are 1, 0 plus 1 is 1, 1 is greater than 1 is 2 is greater than 1. 0 plus 2 is 2, 2 is greater than 1. But 1 is not greater, so 0 plus 1 is 1. Yeah, I think it's that. So skip it if it's too long. And then now to check if this matches. Mm. So this is just the wrong way of doing this. I think this is just the wrong way of doing this. Oh, fuck me. So what I should do is I should probably be pulling a substring from the source string at lengths that are possible to be exchanged, and then compare that with the stuff that is in the dictionary. Yeah. So maybe unique length should be a set. Unique length should be a set. Add it to the set. Okay. So it's actually base. So from this letter, okay, so I think it's for other length in the set that is unique lengths. Oh, whoops, wrong area. For every what did I just type? Okay, yeah, that's what I just typed. For every other length in the unique lengths, if k plus this other length is greater than the total length, then skip it. And then I look at the substring. So kind of the original sub is the source from k to k plus other length, and the target substring is the target from k to k plus other length, and these must be in the actual dictionaries. If O sub is in all words and T sub is in all words, and there does transition below cost. Let's see. I need to find their indices. I guess it should be something like if, if O sub is in all words, then O index is going to be all words at that index. Else break, I guess. Or else continue. every other length. Yeah, it should continue. If T sub is in all words, then yeah, then T index is equal to all words at the T sub, else continue. Could also do if O sub in all words and T sub is in all words. Or if O sub not in all words and T sub not in all words continue. That's probably just slightly better syntax. This looks really horrible. If O sub not in all words or T sub not in all words. Skip this. Okay, O index is equal to all words at the original substring. T sub is equal to all words at the target substring. I guess I could just make this into single state. Guess I could make it into the same thing here, right? And then what? And then if there is no transition between these two, if low cost between the original index to the target index is equal to infinity, also continue. I guess, yeah, here, do I want to do that? Or do I just want to do the if statement to compare the current cost? Sure, maybe if current costs plus low cost from original index to target index is less than dp at k plus other length. dp at k plus other length is equal to current costs plus low cost of original index to target index. And I think that's it. So that fudge. Oh, I can't actually do this. That's right. Can't actually do this. It's because I could change it and skip over a bunch of stuff between. Like change 5 letters from the start. And then that would change the low cost at, or the current cost at the DP matrix at the ending value. Nothing in between. Everything in between is the cost infinity. I guess maybe how would I break early? I guess I break early if the latest is maybe I track the latest non-infinite one. Oh, I know. It's actually just if the current cost is infinity, then skip it. then move on to the next one. It's probably fine. And then I'll eventually hit something that's not infinity, hopefully. Yeah. I think that's reasonable. Push, push, push. Find the thing that's not infinity, then move on from there. Okay. And then if dp at the last is equal to infinity, return -1. Actually, I guess return -1 if dp at the last is equal to infinity, else return dp of -1. Oh, hopefully this works. Hopefully it's not too slow. Or doesn't crash. Turn -1 if dp, oops, else just me. Hallelujah. Wrong answer, you say. But. Oh, baby. Huh. Actually, kind of oddly close. This is a lot of test cases before this thing failed. I wonder what I did wrong. Every other length in lengths case greater than. It's not possible. Skip from source to target. If the source or the target is not possible, keep on skipping. If find the indices of those words, get the current cost plus low cost plus current cost plus the low cost, dp k plus other length. Oh baby. This is going to be really hard to decipher. I guess I just look at this thing. What happened? There's only 5 things. So it looks like it did some sort of 1-letter exchange here. There's no 3-letter exchange, so it had to do a 2-letter exchange here, and then final letter exchange here. So G to T. So G to T does have some sort of connection, I assume. Odd. There's actually no G to T. How did it do this? How did it go infinite and a number? Oh no, that's okay. I'm misreading this. This is just the final answer. So there is no G to T. This is what the infinity means. I had to do 2 letters at the very end. I had to do some sort of transition between like B, G, or some difference thing here to YT because there's no BG to YT. Or there's no G to T, so I had to do some sort of two letter transition. Alright, so I think I need to know what my matrix looks like. I think, how do I do this? Did I ever use unique words? Guess I never used unique words after I even created it. Alright, anyway, so I'll do unique words. I'll print out the transition matrix, maybe. It's gonna be pretty big. It's gonna be like 20 by 20. Bigger than that. There's, I think, more than 20 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So something like 25 by 25. It's probably going to be too hard for me to decipher. Okay, given that, can I come up with something else? Zero, 20, 44K, 601K, 601K. So looks like maybe the third letters were the same. Yeah, the Y became a Y. So it was F. So basically, it was FJ to AP in some fashion, then BG to YT in some fashion. BG to YT. BG was in the original, YT is in there. So it looks like it'd be interesting. I mean, looks like if there's a staggering here. BG to XR, XR to CC, CC to IP, back and forth until it's YR to YT. Same thing with the single letter, maybe. F to W, W to I to U, U to G, G to A to E. So eventually you get F to A. And then J to... How do you get J to P? J to O, O to G, G to I to U, U to P. So there you get J to P. Okay. 558 versus 332. Time's a ticking. BGXR CC. So the first row here is based on BG. Okay, so I think what I want to do is I want to just break this down. See if it did the first three correctly. So it's either doing the first three incorrectly. Okay. Okay, the second question is it doing the last two correctly? BG to YT. So it's doing the BG to YT correctly, so it's based on the first three that's incorrect. Okay, so let's say the first two, because the Y to Y is the same, right? So it's probably doing this incorrectly. Okay. And then is it just doing F to A correctly? Original 1 less than 1 but 2. Sure. I think it's because there's some things that are size 2 in original changed. So it's doing just the F to A incorrectly. So F to A should just be F to W, W to I to U, U to G, G to A to E. You know what? Is there some sort of duplication here? Let me go ahead and just double check this. So it's, what is it? F W I U G A E F S R P J O G I U. And here's W I U G A E F S R P A O G I U P. Is there duplication here? This is a little hard to read. Oh, was there? Yeah, there's I to U multiple times. I see. Yeah, there was that one thing that I fixed on the previous example, but I didn't really check here, which is the fact that there could be multiple same transitions. So here, K in range N indices. Stupid. If low cost from O index to C index is bigger than exchange cost currently. So stupid. Yeah, did recall fixing something or being quite aware of that possibility last time, but just didn't figure to think about it again. I think I need to get rid of there's more printouts I did. Or is there? No, it's just all there. Alright, this should work. Oh, okay. Wow, that was a good chore. So let's see here. Um, so what's the summary here? So the summary is very much builds off the daily challenge from yesterday. Part 1, medium. In that one, built a transition matrix for all possible letter to letter exchange. Built a transition matrix for all possible, which stored the lowest possible transition cost for that exchange. The difference, or the primary difference is, actually I need to clean up some stuff here. I never use unique words. I did use unique lengths. I think that is correct. Okay. Alright, the primary differences here. Instead of letters, consider the space of words in original and target, since those are the only possible exchanges rather than letter to letter. If there are if all the original target strings are 3 letters, then just considering all those 3-letter exchanges. Or, all of them are 2 and 5 letters, then you're considering all the 2 to 2 and 5 to 5. Create, map each of those possible words into an index, and create an appropriately sized transition matrix. I call this again low cost. Set initial values to the transition, to the positions, the row and columns indices in the matrix based on the original changed and cost array. Also, be wary of duplicates. Only store the lowest cost. So there could be let's say there's two things that are A, B to X, Y. One that costs 5 and one that costs 10. Only store the one that costs 5 into your transition matrix. And then for each starting word or word index, calculate the lowest cost to any ending index, ending change / index. Same technique as yesterday. Use a heap, explore neighbors, update matrix, have a nested for loop. And then last but not least, finally, the biggest new component compared to yesterday. Have a dynamic programming array to store the lowest cost to transform source to target up to a given index. Use a loop to compare, to iterate over the indices and update that DP array based on the possible exchanges from each index. And then, finally return the lowest cost thing found at the end. Alright, so those are kind of 5 main points, very broad strokes. So first idea was creating kind of a transition matrix, just the initialization of it. So I have a all words dictionary, so I can map the word to an index. I have a word num tracker. I have a length tracker, which is useful for some of the other, they'll be useful later. And then for every word in the original, I add that to my all words. Store the basically the index here as the word num, increasing the word num, and adding the word length to the set of all lengths of words. So like the set might be 1 and 2 if all the original and change strings are 1 and 2 length strings. Just helps figure out how many words or the length of words I need to consider. And then for every word and change, do the same operation, have a unique identifier. This is just to make a square matrix. Technically, it could be a rectangle matrix where every original word needs to have an index into row index, but column indices should be every original or changed word, but just to keep it a square, to keep it simple. Then here's the square transition matrix. Everything's by default infinity costing to transition from some originals to some changed. And then iterating over the space of original change and cost entries. Get the original word index and the change word index. So just use the mapping. And then, assuming this is the smallest cost I've seen for this transition, store it. So that just prevents redundancies. Or not redundancies, but prevents stupid extra entries of the same letter to starting to ending words that have different costs. Anyways, so that's just the basic ones, but this one doesn't include the possibility of like kind of cascading transitive exchanges. So for every starting word index, consider all its neighbors. So like let's say A goes to B and A goes to C, then B and C gets added to stack where I'm considering the neighbors of A. Here's a heap, so I'm considering all the lowest transitions. I don't think this is necessary, but just by default, the cost of transitioning from one letter to itself should be 0. And then explore the heap. So consider all the lowest cost stuff first. So take the total cost to get to a certain thing. What is that current thing? And then I don't know if this is necessary either, but for every other thing, other being all the other possible words in the word space of all words, and here it's just the by indices. Ignore if it's the current or the starting index. But in this case, if there is something that connects from the current index to this other index, basically there's a transition there, and it's, well, if it's infinity, then there's no transition, so skip it. But if there is some transition otherwise, then find the transition costs between them. If that transition plus the path to this current is smaller than the path from the start to this other thing, then update, push that to the heap, and then do that heap until it's empty. And this will make it so that the transition matrix has the lowest cost from any starting index to any ending index word. So after that is the main part for this problem, which is the dynamic programming. So you have a length of the target or source words, and then you have a stored cost, lowest cost to exchange all the letters up to a certain index from source to target. Iterate over all the indices. Well, first off, you don't need to exchange the first letter, right? So, or the starting cost, starting is 0. And then for every index that you want to change from source index to target index, get the current cost. If it's infinity, then that means somehow you haven't really gotten to this point with some value exchanges, so skip it. If it is the case that the source and target are the same letters, then you can skip basically. Or one possibility is just push and don't do any exchanges for this index. So if the current int cost is actually less than whatever it is to get to the next letter, is smaller than that, then the smallest stored cost to get to the next letter, then push this cost. And then for every basically possible lengths of kind of exchanges, assuming that length doesn't push this thing out of bounds or out of index, then consider the strings involved for that length from the source index, from the source string to the target string. So if this other length is this 5 letters, then you're going to consider the substring from this index, the 5-letter substring from this index in the source and target, assuming those are actually valid things in your kind of space of exchanges. Then find the indices, compare and then update based on the matrix, right? All right. Time complexity, this can be O of I want to say this is O of n times k squared where n is the length of source / target strings, and k is the total length of the original or the changed. I guess it's length of original plus length of changed, which is the same. guess k is, yeah, length of original plus length of change. Yeah. This is to build the transition matrix. Well, no, that's not right. For every starting index. No, yeah, this is. Oh, wow, I don't know. Is that actually right? What did I say for yesterday's? It's O of m plus n. Yeah, I don't know. I think really unsure. I think overall the dynamic programming part is O of n times, there's O of n here. Yeah, O of n times O of m. Where n is the length of the source target, and m is the length of the sum of original plus changed. But then the creation of the transition matrix should be O of m squared, which is different from what I wrote yesterday, but I think what I wrote yesterday is wrong. Since it has an outer loop and inner loop that should both iterate over all possible indices, word indices. Yeah. Yeah. This is O of m squared to store transition matrix, and O of n to store the dp